that's the second part of the supervised learning, and we mainly focus on the first part is we are talking about rectangle hypothesis, right? And also the last week we talked about PAC learning on given the rectangle hypothesis, right? So now that we talk about given the rectangle hypothesis, that what we should be doing if we consider a noise-free situation. So now we consider the noise. So then also some other situation, okay, such as the multiple classes. Then what we are going to do, right? So of course the noise, when we say noise, right? So I think you should understand that if we don't have noise, so everything should be not just like simple, actually it should be like trivial, right? Because if we assume there's no noise, right? So all the data we should pay attention to, right? So which means that there's no such thing like overfitting, right? Okay. We didn't really like carefully talk about I think we talked about overfitting already, right? Where? I mean, not here, of course, right? It's like the first time to be here. So we talk about overfitting. Where we talk about overfitting? Anyone? Maybe no, right? Do we talk about overfitting right here in this class? Maybe you knew it before, right? Yeah. I mean, so you are perfectly okay if you don't remember anything, right? Okay, I thought that I talked about, you know, but actually the second part. So actually that belongs to the second part of the decision tree, right? So if you check the decision tree video, we only cover the first part, but the second part is not yet, okay, not yet uploaded. So what is overfitting? So what is overfitting means that people may have some kind of misunderstanding, right? But actually overfitting we can say in the following, right? So later we're going to show more things. So overfitting means what? Overfitting means that when we have a model, when we have a data, right? So data these days, data could be very, let's say, complicated in the sense that if we talk about autonomous driving, right? So data could be, let's say, a lot of different, we need to cover all kinds of diversity, right? Like for autonomous driving, then we talk about sunny days, right? Raining days, snowing days, maybe, right? The daytime, nighttime, during the dawn, let's say during like the evening, right? Maybe the lighting from different and the sun from different direction, right? All kinds of situation, right? Will be very, very difficult, to be honest, right? So we need to cover all kinds of diversity, right? And that's the data, right? At the same time, we also need to make sure the model is complicated enough to deal with all kinds of diversity from the data and from the concept, actually. So when we say, okay, when we say model is more difficult, model is more complicated than the data, more complicated than the data, we say is overfitting. In other words, we say that the model is unnecessarily complicated, right? We say it's overfitting. Okay, we say it's overfitting. I think we can easily give you one example right here, this one. Okay, in fact that belongs to some later situation that we want to talk about. Let's say for the regression problem, right? The regression problem means that we talk about classification, we could talk about regression, right? So classification means that what we want to predict is some kind of categorical y, right? The regression is the case that what we want to predict is numerical y. Okay, so and then that'll be the regression problem that we all learn a lot in our high school, right? Such as that, given all kinds of data points, right? So the high school usually what we learn is the linear model, right? Linear model try to interpolate, right? Try to go through all kinds of data right here, right? Which is not that easy, right? So then we try, you know, the data. Sorry, then we try the model with more complexity, right? Such as that we go from the linear model, which is a degree 1, right? So degree 4 is more complicated, right? More complicated means what? Means that the model more complicated means that basically we can say the model is associated with more parameters, right? Okay, then we go here, right? But in this case, that's the perfect situation, right? But we don't know, of course, right? We don't know what could be the true model, right? Maybe we go unnecessarily to be more complicated, right? Meaning that we try a model with more complexity, meaning that in this case, higher degree of polynomial, right? Okay, then we come up with this kind of polynomial, right? This kind of model. Then yes, of course, for the data, input data, we perfectly fit for all the data, right? But what? But it doesn't mean that it's a good model. Can you tell me that why is not a good model? Can you tell? Based on, you know, the limited information. Do we know why? Can you say why it's not a good model? So here we talk about noise, right? We talk about noise, okay? So noise means what? Means that the data points will be not perfect, right? Okay? If the data is perfect, then what? Then we should try our best to fit those data, right? Which means that the model that we have should what? Should go through all the data points. Okay? But we didn't, right? We didn't try right here, right? Like this data point, right? We didn't let the model go through, but we still think that the model is good enough, which means that the model could be slightly different from the data points. Meaning what? Meaning we don't really trust the data 100%. Okay? Yeah, so that's the noise. So the situation I just mentioned, that if the data that we assume is noise free, right? The model is so easy. The trying to find a good model is so easy, right? Because we never worry about overfitting. We never worry about overfitting. Is this case we talk about overfitting, right? Meaning that the data we assume is like degree 4, right? The model is degree 15, right? Which is unnecessary complicated, right? So we say overfitting. Okay? So I just mentioned what statement? I just mentioned that if we don't have noise, right? Usually we don't need to worry about overfitting problem, right? Because whatever data that we have, we should just say, oh, that's what we should pay attention to, right? Because whatever data, right, even just one data out of 1 million, right, we still think that the data is very important by all means, right? So then we need to feed the data as much as we can, right? Yeah, but that's not the case, just because we know that some of the data is kind of noisy, right? So we can just simply ignore, okay? Could be ignore 100%, meaning that the data could be, for instance, could be one data right here, right? Okay, we ignore almost like 100%, right? Or maybe data is right here, but it's like a little bit different from, deviate from the model, but we think it's okay. Yeah, so that's noise, right? Okay, we'll come back to this right away. Yeah, so we talk about noise, right? Okay, unwanted anomaly. So in fact, that noise will be more than just one kind of noise, right? Such as that we talk about measurement error, right? So before now, we just talk about measurement error because the data, right here, maybe we can be more specific. Like if we talk about classification problem, here is classification problem, okay? We didn't move on to talk about regression problem yet, right? So for the classification problem, if we have noise, there'll be, if we have error, if we have noise, there'll be a list of two kinds, right? So either that we have, okay, either that we may have the measurement error, meaning the error from X, or we have a teacher error, meaning we have the error from Y. Okay, so think about this situation. If there's a noise, right? So before now, let's say that's the rectangle. Suppose that's the best hypothesis, right? Okay, but now we consider there'll be several imperfect situations, such as we have the negative here, right? And also we have a positive here, right? Okay, so it could be measurement error, meaning what? Meaning that the it's negative for sure, right? But the negative, just because we measure the negative in the wrong way, I mean, there could be the negative should be shift to in this direction or in this direction. Basically, should be outside of this rectangle. Okay, so that's what we say measurement error. And also right here, right? It could be just we measure the y in the wrong way, so it should be right here. Who knows? So that's what we say measurement error, right? On the other hand, it can also be what? The teacher error. Teacher error means that we call them in the wrong label, right? It should be negative, should be positive. Okay? So what is difficult here, right? It's just because we don't know it's noise. Yes or no? If we know it's noise, forget about them. Okay? Forget about them. I mean, or modify our model or whatever. Depends on its measurement error or teacher error. Its measurement error, we allow a little deviation from the bounding box, from the border, the boundary, right? If it's teacher error, that means we can just simply switch the label, right? Okay, but of course we don't know. Okay, so when there's a noise, there'll be all kinds of situation, right? Okay, okay, the noise gives us the situation like we cannot perfectly do our job, right? We cannot have a perfect hypothesis. So I just mentioned, let me just try again, is that if we don't have noise, everything is so easy, so damn easy, right? But if we, that's not the case. Most of the time we have noise. Okay, so noise prevent us from perfect hypothesis, building perfect hypothesis, right? There'll be also some other situation. It's not just because noise. It's because like we don't have enough information, right? Such as that we have something hidden, something unobserved, right? Or something that, let's say the feature could be 20, that we give them like 18, right? There'll be two things that we're missing from our observation, right? So in this situation, we cannot easily predict everything perfect, right? So that's also some situation. It's not we say noise. It's like but it turns out to be like noise. Turns out to be like noise. You got that? Okay. Yeah. So just because we don't have enough information, right? So everything could be a little bit vague, right? Like if we don't have enough information, if we only use what we have, the things could be a little bit dilute, right? I mean, could be a little bit out of the norm, right? So deviate from the norm, right? So we don't know what's going on. It's like a noise. It's like a measurement error in some sense, right? Okay. So for all kinds of situations like this, then we have to know how to deal with them, right? So the situation is, okay, basically two choices. Either that, so when we have noise, so suppose this one is noise, suppose this one is noise, and basically we don't know, right? So we have two choices, right? Given such a new data, right? Either that we are going to what? Change our model, or we stick with the original model somehow, right? Or something in between, right? If we try to modify our model, that means what? We consider them as a real, I mean, something serious data that we have to pay attention to, then we need to modify our model to be something like this, right? Okay, more complicated than before, right? Before now it's rectangle, now we like the curve model, right? Why is it more complicated, right? Because when we need to refer to this model, when we need to build this kind of model, we know we need a lot of parameters, right? The model parameters will be suddenly increase a lot, okay? So that's a price that we have to pay, okay? That's a price we have to pay in what? In the training and also in the testing. Okay, in the training means that we have to collect more data to make sure that we can predict, we can fix the parameter perfectly, right? In the testing means that we have more, usually it takes more time to find out what? If it's a curve model, right? You know that the testing will be like longer, right? Okay, what does that mean? Do you know? So if it's original, right, the rectangle, we to check inside or outside, we just need to check P1, P2, E1, E2, right? To make sure that it's inside this box, right? If it's what? If it's this curve model, how to check? So you can, one situation you can assume what's the curve model. The curve model could be the intersection about a lot of linear model, right? Think about here, it will be linear. A lot of little segment all combined together, there'll be the curve model. Okay? Then how to check? One linear model here. Maybe we can just try to see if we can draw something, right? So it could be linear model here, right? Linear, right? Linear, right? Right? So all kinds of linear model like this combined together. So every time you see the linear model, right, you make sure that, you know, inside direction, right? Okay? Then we check, we know that's inside, we know it's positive, okay? So you know how much time that we need, it takes to complete all kinds of tracking, right? Okay? So that's something not so easy, right? Not so easy. So when we have, when we go from the simple model to curve model, it's like a trade-off, something that we need to think for a while, right? Okay? Yeah. On the other hand, maybe we can simply say, oh, that's noise. Then let's just forget about that, right? Then let's wait until what? Until more things like this coming, right? So if there be a lot of data accumulated around the what we call the noise before, right? Then we know something going on, right? Okay, there will be more data here, more data here, more data here belongs to positive, more data here belongs to negative. Then we know we have to give up our original model. Okay, so the quote is hard decision, right? It's a hard decision between choosing zero training error, okay, but with a complicated model, or little higher error but with simple model, right? So that's, I mean, even for the professional, right, they don't exactly know what to choose, right, in general, right? So what you need to learn from this class or from machine learning discipline is that when we are experience more and more situations, right, cases, we deal with all kinds of real data, right? We know how to make the smart decision right here. Okay, so that's what we need to deal with the noise. And also I mean, why we prefer simple model, right? Okay, there's a lot of reasons for that, right? Such as that maybe easy to classify, right? Meaning the testing is easy, right? Easy to explain, right? And I think we know that, right? Easy to explain because when we don't have a lot of rules, right, things will be easy to understand. Who can be understanding here, right? Your boss, right? Later, if you build a model, you need to explain to your boss, right? You have to be clever, right? Because when you can explain it well, you get what? Increase, right? About your salary, right? Okay, fewer parameters, right? Easier to train, right? I just mentioned that. And lower variance, what does that mean? Lower, I think we can also go to the regression problem here. I just mentioned that how to say this model is not so bad, not so good. One thing that we can say is high variance. High variance can be measured in many ways, right? So we can say one way, we can see a lot of fluctuation, right? Like right here, right? When the data is not too many, right? Right here. So we see a lot of ups and downs. Okay, so no good, right? Okay. One way. The other way is that if we try to modify the data, just change a little bit, right? Then the model change a lot. No good. Okay, I think you can imagine that given our background, right? If we change the data right here or right here, right? Just move the data a little bit, right? So we are going to see could be very different model in the end. So no good, right? So that's what we say. That's what we say. Variance. Okay. Usually we love the model to be associated with low variance. Okay, yeah, usually people don't pay a lot of attention to this part, right? But I think you got the intuition, but just usually we don't intentionally make in this way. Okay, so there's a theory for this. Okay, high bias, that's kind of looks like this one looks like a bad thing, right? Bias, right? I mean, looks like a bad thing, right? But you know, in this field, right, the bias is kind of neutral, right? I mean, it's a good in one way, but bad in another way. Depends on how you view this one. The bias means what? Bias means it's first of all, it's different from the statistical bias. Statistical bias means that we you how do you know this bias? The bias here is different from the statistical bias, right? I think one way to say, we can try again. What is statistical bias? Maybe we can try. Okay. If you remember that if we learn calculate the variance, okay, for let's say for distribution, right? So usually we try what? We try the summation x. Suppose xi will be the data, right? Like this, right? We compute when we compute the variance, right? And here, number of data is n, right? Usually we try like this, n minus 1. Okay, if you still remember, right? From maybe 2 years ago, right? Like you learn probability and statistics, right? When we learn how to estimate variance, right? It could be like this one, right? Okay. So we the denominator is n minus 1 instead of n, right? If we try n, that will be what? That would be underestimate. So we try n minus 1. Okay. I think maybe if you joined our class before, sometime in your lifetime, right? So maybe you heard about my way to explain this, right? So when we have data, suppose it's like like one dimensional, right? So we have a 1, 2, 3, 4, 5, right? Okay. Yeah, suppose this one is the mean, right? Suppose this one is the mean. Okay, sort of, right? Okay. So when we compute the variance is like what? The average distance to the mean, right? Okay. So how to calculate this one? So we are going to say calculate what? Calculating what? If we divide by 5, right here, 1, 2, 3, 4, 5. So here is like we either divide by 4 or divide by 5, right? Okay. So what we say, the unbiased estimation. Unbiased means that given a lot of them, right? So we say basically we don't overestimate, we don't underestimate. Unbiased means that what we want to predict is the right thing, right? Okay. So unbiased estimation is divide by 4. Okay. So how to divide by 4? I think intuitively you can imagine that we have 1, 2, 3, 4, 5 points, right? If we calculate the average of the distance, average of the data to the mean, the distance, average distance to the mean, right? How many data points we should calculate? 1, 2, 3, 4. Not itself. Okay. So that's how that we divide by 4 instead of 5. You got that? Because if we divide by 5, that means what? This one to the mean, the distance is 0, right? So which means that when we visual the things scatter all over the place, right? We kind of think, the gap should be what, right? But the variance is okay. If we divide by 4, divide by 5, they'll be smaller, right? I kind of give you some kind of my way to explain why we need to divide by 4, right? Because the other data is 4 of them, right? Not considering the mean itself. Okay. Anyway, So that's the bias from statistics. Here, the bias is the other different meaning, okay? Don't get confused. Here, the bias is something that we have to make sure that the we can predict things. We can predict things. So what does that mean? So given the model, rectangle model, okay, we say what is the bias? Bias is what? Okay, first of all the machine learning model, all the machine learning models, I think one goal that we can try is what? We say what? We want to go from what? Okay, from data, okay, to what? To model. From data to model, I mean that's training, right? So this training, in the end, we need to make it to be, let's say, programmable, right? We need to make it we need to write a code, right, which is what? Deterministic, right? Okay, how can it be possible? The model and data, they are not equivalent. What does that mean? So model is so powerful, data is less powerful. The model, when we have a model, we can what? Do everything we want, right? We can predict in all the area, right? So if we have a model, right, so assume that that's the true model, right? For every place, all over the place, we can predict either it will be positive or negative. So that will be more powerful than, no matter how many data that you collect, they'll be more powerful, right? If you know the model is perfect, right? Which one you want? Model, right? You forget about the data, right? So it's not equivalent. It's like we want to go from something less powerful to something more powerful. Not possible. Not possible. We have to do what? Make assumption. We have to make assumption, right? Okay, we have to make the assumption. Here, the assumption is what? Rectangle hypothesis. Okay, rectangle hypothesis. We assume the model is rectangle. Okay, that's the bias. That's the bias. Okay, the bias says what? The bias says, okay, even we don't know the truth, we assume it must be something. That's the bias. So bias is somehow equivalent to assumption. Okay, the bias is somehow equivalent to assumption, meaning that even that, so we say, oh, here, can you call there's a data right here, that's positive or negative? We say, oh, negative. How do you know? How do you know? Oh, I mean, actually you don't know, right? The model could be like this, right? Could be like this. Who knows, right? Okay, but we say, we tend to say that's not the case, just because we have bias. Okay, the bias in this case. So if we want to go like a derivative process, usually we say what? The data, okay, cannot go directly to model, okay, because it's going from something less powerful to something more powerful. Okay, it doesn't sounds right logically, right? But with bias, if we with bias we can do that. Okay, so bias is something that we add to the model so that we can go from data to model. Oh, sorry, bias is something that we add to the data so that we can go from data to the model logically. Okay, logically means what? Means that if we want to go from data to the model, usually what we call what? Induction, right? Induction is not a logical process. It's not a logical procedure, right? Because everybody can have different hypotheses, can have different model, right? based on the same piece of data, right? So that's not logical, right? There's no any like statement that can tell us that we must have this model, right? No, that's not possible. So what is missing? We have to add something to make it possible. What thing to add? Bias or assumption. Okay, got that? So the usually what we in the end, okay, high bias means that for a simple model means what? Means that actually we add more assumption. Okay. The on the other hand, complicated model means that we don't have a lot of assumption. Okay. So you can imagine that the deep learning, right? Deep learner is somehow with very few assumption, very few bias. Okay. Yeah. Okay. So theoretically, even I didn't say different in detail, but what we want is to minimize variance plus bias. We want to minimize the variance plus bias. Means that we don't want to introduce a lot of bias, okay, a lot of assumption. At the same time, we also want to make sure that the variance is not so big. Yep. Okay, and later we talk about Occam's razor. Occam's razor is like we want to make sure that the model is not too complicated. Okay, given the data, right? We don't want to introduce unnecessary complexity. So that's Occam's razor. Okay, so yeah, the 1 hour is too short. Yeah, maybe we can just finish this one, and then for the rest we talk about that tomorrow, right? So multiple class. If we have multiple classes, then so multi-class problem. Okay, one situation maybe you can say, oh, if we want to separate between, let's say, recognize between, let's say, 0 and 1, right? That's binary classification. Multiple means that the 10-digit problem, right? Or if we talk about a more complicated situation, is like to recognize Chinese characters, right? That be multiple classes. So something that we have to pay attention to is that when we go from multiple classes, from binary to multiple classes, we have to try some strategy, right? Such as that here that we have 3, right? Okay, 3 classes. That's very easy, but good enough for us to make to give some we can have some discussions such as that. Okay, can we still use binary classifier to help us? So that's the situation. Can we use the binary classifier? Okay, the thing is that we can use a few of them. Okay, like we have 1, 2, 3 class, right? If we want to use binary classification to help us, then we can try, basically we can try, there'll be just yeah, actually there'll be just more than just a few strategies here. So one is 1 against rest, right? So every time we say, oh, is this here is, suppose there'll be 3 kinds, right? Like a sports car, right? Luxury sedan and the family car, right? So if we want to separate these 3 different categories, right, then we say what? Oh, we take turn to say, oh, is this sports car, yes or no? Or this luxury sedan, yes or no? Or this family car, yes or no, right? 1 against rest, 1 against rest. Okay, so basically we need to introduce when there be k class, we say, oh, k different 2 class problem, right? Okay, we try them all, right? Okay, then what? Then I think we can come up with something like a confidence value, right? We say, oh, we take turn to check for each of the class, actually each of the classifier, right? There'll be many of them, right? So which one say yes? If there's only one yes, then bingo, right? If there will be more than one, right, we say which one give us the highest confidence value, right? Okay. On the other hand, if everyone say no, right, which one give us lowest confidence value, right? Okay. So that's one strategy. The other is like two class problem, making it to be take turn to be one against one. One against one means that there'll be k of them, right? We choose two. Let's say between sports car and sedan, we make a linear, we'll make a separation, right? Okay, in this case a rectangle, but it's not perfect to use rectangle here, right? Suppose we try linear separation, for instance, right? Okay, so for each two classes we can try linear separation. So there'll be k choose two, so many to try, right? Then in the end we try voting. Okay, we try voting, right? So between this A and B, we say, oh, it's more like A, right? Between C and D, we say, oh, it's more like C. Between B and C, right? We try all of them. Then voting give us, okay, which one receive more votes, right? Receive more votes. I think that could be the true answer, right? You got that? Did you get it? Yeah. So which means that, so if it's sports car, right, then we are going to say what? We are going to say, okay, so yeah, first of all, maybe between these two, right, we say it's S, right? Between sports car and family car, so we also say S, right? Then we got 2 votes, right? Okay. So between family car and sports, the luxury sedan, right? Either way, right? So sometimes maybe we also get more votes, right? So if we have more votes, there'll be the truth, right? Okay, quite likely. So and also we can maybe two more minutes, right? So we can also say, oh, maybe we want to introduce a exception class, meaning that none above, okay, belongs to anything else, doesn't belong to any of these classes, right? Okay, depends on what we want to do, right? So if there's a data right here, right, we're going to say, oh, it's more like family car or sports car, or maybe we say none above, right? Or we say, oh, we don't have enough information, we don't have enough confidence, we just say we don't know. Okay, that's also possible. And in between those different procedure, right, the strategy that we try, especially for this one, okay, we may introduce unbalanced situation, one against rest, right? If it is a one against, let's say 1,000, right, 999, right? So okay, if we try one against rest, right, then it could be unbalanced situation. Okay, we also have to deal with this. Yep. Yeah, so that's all for this part. Okay, so see you tomorrow.